Something else we observe is that the sunspots come and go. So here, for example, if you follow the sun, if you look at the features, here it's relatively smooth, and as time goes by, you notice that the sun is going to become there's more activity, and then the activity diminishes until it looks the same as before there. So there's this cycle here of solar activity. And what we find is that this cycle of solar activity is linked to the number of sunspots that you see. So there's something called a sunspot cycle. Where for a period of time you don't see any sunspots, and you see a maximum, and then it disappears, and then it repeats again. And the cycle lasts 11 years. And so we've been tracking these sunspots since, you can see here, since the 1600s. And they have some interesting implications. So here you see that the sunspots are cyclical. You go from a maximum to barely any, to none, to a maximum again, and to barely any. And if you try to look at how long these cycles last, they're going to be about, when a scale here, just estimate about 10 years or 11 years. And so this is a longer stretch of the sunspot cycles. And something interesting happened. In the 1700s, there was a period of time when they observed a minimum of the sunspots, and it's lasted for let's see here, for I guess almost 100 years or 50 years or so. And at the same time period, northern Europe became colder than normal, and this is called the Little Ice Age. And this is in this period called the Maunder Minimum. So solar activity, or the sunspots are related to solar activity, and it can affect us here on Earth by causing the climate to cool down. So what causes these sunspots, or this activity to come and go, and a sunspot to appear and then disappear? What causes it is something similar, an effect similar to what we discussed with Jupiter. When we looked at Jupiter, we said that at the equator, Jupiter spins very fast, and at the poles, it spins very slowly. And the same thing happens with the sun. So the sun, just like Jupiter, well, more than Jupiter, is a complete ball of gas. So what you find is that the sun rotates at different speeds at different latitudes. And not only that, the sun has its magnetic fields. And as the sun rotates, the sun actually starts to bend and warp its magnetic fields. And because it rotates at different speeds, what's going to happen is that eventually the magnetic fields are going to develop kinks, and they're going to start to become twisted on top of each other. It's just like a pipe here. So once these twists occur and you form knots, what happens? So you can actually see an image here of the magnetic fields. It looks like a tangled web with magnetic fields around the sun, but you can clearly see loops there. But as soon as the loops go from being like this to forming a knot, as soon as that knot is formed, it kind of breaks that loop, and it creates an explosion or a release of energy. And this mirrors the appearance of the sunspots. So as soon as you start to form all these knots, you have maximum solar activity, and then all the knots or these magnetic field knots are broken, and then you go to seeing no magnetic fields or no sunspots, and then this cycle just repeats again. So the next thing is what happens once you get these knots. So you have again here a plain old magnetic field loop. As the sun spins around, it starts to tangle those loops, and as soon as the loop gets tangled like this, at that kink there, that kink is broken off, and you get a release of energy. So that's the next thing that we're going to look at. So these releases of energy, these are called flares or explosions. So on the surface of the sun, a flare is an explosion. It's not a loop like the prominences. And these explosions, they can be 6 times hotter than what happens at the core, and they last for several minutes. And what's happening here is that the loops or the prominences, the particles are trapped inside these loops. They can't go anywhere. But at the flares, the particles are ejected out into space. So the flares eject particles into space. So you can see here a flare developing and exploding. So where does this stuff go once it's ejected? So here we're going to go back to something that we talked about before, which is the corona. So here, this is an X-ray image of the sun's corona. And what you find is that there are actually holes in the corona. There are gaps here in the corona. And what these gaps are, what we believe is that, and normally magnetic fields they form loops, and these loops trap particles. They can't go anywhere. But wherever these loops are broken and the magnetic fields are just, falling out into space, so their particles are free to fly away from the sun and escape the sun. And these openings occur in the sun's corona, so we call those holes in the corona, or coronal holes. So once you have the flares, the next thing is that you have holes in the corona, or coronal holes. And the ejected particles blow out of these coronal holes as solar wind. So solar wind escapes through the coronal holes. And what's escaping is not wind, but streams of electrons and protons that are that are being ejected from the sun. So actual matter. And you can see the explosion here. So the sun is blocked out, or part of the sun is blocked out here because it's very bright. But you can see matter being ejected from the sun here. So these are called coronal mass ejections, because what's being ejected is not just light, but streams of electrons and protons. And as this cloud of ejected protons and electrons moves towards the Earth, depending on how its magnetic field is oriented, it can impact the Earth, and the particles can stream into the Earth's poles. And we'll see what's going to happen on the next slide. And so what can happen is that once those streams of electrons and protons hit the Earth's magnetic field, they get trapped by the Earth's magnetic field. And as they do, I believe you mentioned that before, whenever charges spin around or vibrate, they emit light. And this is what you see as the aurora lights over the north, or the northern lights. Not only that, these same coronal mass ejections, they're streaming charged particles. They can interfere with satellites and communication systems as well here on Earth. And so now let's look at this amazing, to put all this into perspective. So the energy is created at the core of the sun, and it travels outwards as radiation first, as bouncing like a pinball machine, and eventually it cools down to the point where atoms can form, and there the energy travels outwards as convection until it reaches the surface of the sun, and then it can fly away. But what you notice here is that this doesn't happen immediately. It can actually take the light from the core over 100,000 years to reach the surface. And to put this into perspective, or at minimum, almost 10,000 years. So put this into perspective, light that was created at the sun 10,000 years ago, so that corresponds to when the Earth was covered with ice during the last ice age, when humans were still interacting with ice age animals like saber-toothed tigers and mammoths, and even when humans were interacting with Neanderthals. So when these ancient humans were around and these ancient animals were around, a particle of light was created, and you can look at it. You can see that same particle today when you're looking at the sun. So the light that you see today from the sun was created when Neanderthals and mastodons were around, and when the U.S. all the way down to Michigan, for example, was covered with ice. Or it can even take longer than that.